You've seen a few times now that the histogram of the binomial distribution starts to look normal as the number of trials increases. And you know the normal curve rather well. You know how to use it from stat 2.1x. And so what we're going to do is examine the binomial more carefully to see if you can use what you already know about the normal to quickly get at some probabilities that might otherwise take a bit of computing power to work out. And the one thing we've not really looked at with the binomial is its standard error. We know its probability function and we know its expected value. The standard error, that is the spread of the distribution, is worth examining now before we get into the normal curve. So what's the binomial distribution? It is the distribution of the number of successes in independent repeated success-failure trials. And in terms of box models, a random variable x has the binomial distribution if it's the sum of draws at random with replacement from a box that has only ones and zeros in it, a proportion p of ones, and the remainder of zeros. So we first examine this box, and we've done that before. The average of any 0-1 box is the proportion of ones in it, so that's just a recap. What's the SD of this box? Well, this is just a list of numbers. There's a proportion p of ones and 1 minus p of zeros. And so what you want is the root mean square of the deviations from average. Well, what are the deviations from average? That's the average. That's one of the numbers, 1. So a deviation will be 1 minus p, and the other deviation will be 0 minus p. And so when you compute the SD of the box, the calculation that you will end up with looks like this, and let's take a look at the bits of that. So here's a value 1, the average is p, the deviation is 1 minus p. You're going to square that deviation, that's what you got there. And there's a proportion p of those. Play the same game here. The value is 0, the average is p, the deviation is 0 minus p. Square it. There's a proportion 1 minus p of those. And this is the SD of the box. Well, fine, there's an awful lot of p's floating about here. Let's see if we can simplify anything. And one thing I'm noticing is that 0 minus p is just minus p. And then when you square that, you'll get p squared. So let's make that a simplification first. I've left this one exactly as is. And the 0 minus p all squared is just a p squared. So if we look at these two terms, then both of them have a 1 minus p in them, and both of them have a p. So I pull that out. There's the p and the 1 minus p, and what's left? Well, this part has an extra 1 minus p, that's right here, plus this part has an extra p, and that's right here. But when you look at this, 1 minus p plus p, that's just 1. And so what you are left with is that the SD of the box is the square root of the proportion of ones times the proportion of zeros, one of the most famous formula in probability and statistics. And if the algebra made you glaze over, that's okay. Please remember that the SD of a 0-1 box is the square root of the fraction of ones times the fraction of zeros. So what? Well, we're trying to examine the binomial, and the binomial is the sum of n draws from this. And what do we know about the standard error of the sum? We've got a formula. It says you take the root of the number of draws and you multiply it by the SD of the box. Well, we just found the SD of the box, and the number of draws is n. And so the standard error of your binomial variable, which is the standard error of the sum of the draws, is root number of draws times the SD of the box. And you've got the square root of a times the square root of b, that's the square root of a times b. And so the standard error of a binomial random variable is the square root of n times p times 1 minus p. np 1 minus p, in probability it is affectionately known as npq, just because we can't bother to say the 1 minus p. I'll try to say the 1 minus p, but there is going to be the moment when I lose discipline and say q instead. So here is a useful summary of what we know about the binomial distribution. So random variable x has the binomial distribution with parameters n and p. Translated into English, what does that mean? Well, one way of looking at it is to say that x is the number of successes in n repeated independent trials, etc., which we've said before. And another way to look at it is that x is the sum of n draws with replacement from a 0-1 box, with a proportion p of 1s in it. And what do we know about x? We know its probability function. So we know that the chance that x is equal to k is computed by this formula here, which we've discussed at length and you have used a lot. We know its expected value. We know that the expected value of x is the number of trials times the proportion of success, NP. And now, based on what we've just done, we know it's a standard error. So the standard error of x is the square root of n e 1 minus p. In other words, you expect x to be np, give or take, root np 1 minus p. And that's all fine with the letters, but it would make much more sense and be more concrete if you have some numbers in front of you. So let's take the most famous example, the number of heads in 100 tosses of a coin, which you have studied quite a bit in previous examples. And so this has the binomial distribution with n equals 100 and p equals 0.5, no surprise there. Probability formula written out longhand, all that's happened is the 100 has replaced n and 0.5 has replaced p. Now, 100 choose k can be a very, very large number. And so if we can avoid computing this, even avoid asking a computer to compute this, we will. So what else do we know about the binomial? Well, we know its expected value, n times p. The expected number of heads in 100 tosses is 50. We've been saying that over and over again, no surprise there. And the standard error of the number of heads is, by our new formula, the square root of number of tosses times fraction of ones, fraction of zeros, probability of heads, probability of tails. And that turns out to be 5, and this is an answer we had got before by doing the calculation longhand. So the expected value is the center of gravity of the probability distribution. It is just like the average of the histogram. This is just like the SD of the histogram. And what's the shape of the histogram? You've seen this shape before. And the shape is normal. That's what we saw in the last segment. And you know very well that there isn't only just one normal curve. To specify a normal curve, you have to specify its center and its spread. Its mean and its SD, and mean 50, SD 5 is the normal curve. That is the approximation to these probabilities. Do we believe that? Well, I think we should just draw the histogram and see what it looks like. Here we go. So what is this a histogram of? Well, you've got the number of heads in 100 tosses of a coin. This is a probability histogram. Areas are probabilities. And over it I have superposed normal curve, but for now just look at the histogram, the bars of probabilities. You can see they're beautifully symmetric and bell-shaped. And we've said before, and I will repeat, that you can in principle compute each one of these areas. This central bar here, its area, is the chance of 50 heads in 100 tosses of a coin. 8% roughly. We did that when we were doing the law of averages. This is the chance of 50, is it 4 heads? Yeah, something like 54 heads. And you can calculate that by the binomial formula. So there is no mystery to how these heights have been arrived at. You could do it if you had the patience. And you can see that it looks like the bell curve. Which bell curve? Well, this one. Centered where? 50, the mean of 50. Do we believe that this curve has an SD of 5? What's the SD of a normal curve? It's the distance between the center and the point of inflection. So 51, 2, 3, 4, 5, it's not so unreasonable to think that the point of inflection is somewhere there. So 50 plus or minus 5 does seem to be exactly the right scale here, especially when you go 50 plus or minus 10, 2 standard errors away, and you're picking up what certainly looks like 95% of the curve. 3 standard errors away, 65 and 35 on this side, you've picked up almost everything. That's very normal-like, and that is precisely a discussion that we've had before. So the normal curve approximates rather well. You can see that it's above the histogram in places and below in others, but overall, if the pluses and minuses cancel out, it's going to give you very decent approximations. Approximations to what? Approximations to probabilities of ranges here. Now, some of you are thinking that why do I need to approximate? I've already got a probability calculator in my online textbook and I'll get the exact value. Well, so you should if you have your online textbook with you and the problem is of a size that is modest enough for your online textbook to solve. But if the problem is too big for your online text, or if you happen to be without your online text, you should still have a sense of what these probabilities are. And the good news is that you can easily get that sense based on what you already know. So let's do an example. We're going to find the chance of getting between 45 and 55 heads inclusive. And here's me being very persnickety. Why? Because had I just said between 45 and 55 heads, there would have been 500 posts to the forum saying, well, does that mean do I include 45 or do I start at 46? This is ambiguous. Indeed, the 500 posts would be correct. It would be ambiguous to say between 45 and 55 without explaining what I mean to do with the edges. So I am saying inclusive here to mean that I include both of these ends. In other words, I'm looking at a number of heads 45, 46, etc. all the way up to and including 55. And I want the chance that the number of heads falls in this range. So what should you do? Well, you can by hand apply the binomial formula to each of these and add up. Or you can go to your online calculator and just put n is 100, p is 0.5, and then greater than or equal to 45 and less than or equal to 55, and you will get a chance of 72.87 something or other percent. Fine. So what is the new thing that we're going to do? What we're going to do is we're going to see how close we can get to this probability by finding an appropriate area under the normal curve. Which normal curve? The normal curve that approximates the probability histogram. And this is a picture that you have been looking at every single day that you have worked on Stat 2.2x. Do you recognize that? Yep, it's the course logo, and it is also the binomial histogram for n is 100 and p is a half. And it just happens to have shaded these yellow bars, the bars 45, 46, 47, 48, 49, 50, 51, 2, 3, 4, and 5. It is precisely this yellow area that you are trying to find. The online calculator says it's 72.87 and a bit percent. What does the normal curve say? Well, so I was making a logo for a course, so I took out the labels and so on because I didn't want the logo cluttered, but let's put them back in. Same picture, the probability histogram for the number of heads in 100 tosses, and we are looking for the chance that you get between 45 and 55 heads, including both of those ends. So that is exactly the area of these 11 yellow bars. What if I wanted to approximate by the area under the normal curve? Well, then I would be looking at the area under the normal curve, starting at this edge here, where the yellow ends, and then ending at this edge here where the yellow ends. And let's take a careful look at the horizontal axis as to exactly what points those are. So this is the bar over 45. So is this edge here at 45? It is not. The bar is centered at 45. Why is it centered at 45? Well, because discrete histograms, we've centered them that way precisely so that this normal curve, which peaks at 50, is at the physical center of the histogram that we have drawn. This curve, this particular picture, is an example of the reason why discrete histograms are drawn the way they are. So then what is this point? Well, the center of the bar is 45. That's the edge of the bar. Surely that's 44.5. The center of this bar is 50. That one's 49.5, and the other edge is 50.5. So the right edge of the yellow is at 55.5. The left edge of the yellow is at 44.5. This observation is called the continuity correction. You are using a continuous curve to approximate a discrete histogram whose bars are centered over the values. And so you have to take into account the edges of the bars. And so in practical terms, what are you doing? Well, so here's how you carry out your approximation. You've got a binomial distribution, and you want a chance of a certain range. Step 1, figure out the expected value and the standard error, the center and spread of your curve. Now you've got a large number of trials, you believe the normal approximation is good. So now what you have to do is to use the normal curve to find a certain area. And how do you do that? Well, it's coming back from the midst of Stat 2.1, you have to convert to standard units so that you can use the standard normal curve that is tabulated for you, in your case, in the normal probabilities applet that you used so frequently back in 2.1x. So what are we going to convert to standard units? We are going to convert the edges of those yellow bars that we said were at, not at 45 and 55, but at 44.5 and 55.5. That was the continuity correction. So you convert to standard units. You convert to the z's, so value minus the mean divided by the SD, as before. That happens to be minus 1.1. And then the second one, on the right-hand side, the value minus the mean divided by the SD is symmetrically plus 1.1. And what you want is the area in between. And so you use your applet, and you put in minus 1.1 as your left end, 1.1 as your right end, and what does the applet say? The applet says 72.87%. Now, isn't that remarkable? Because the exact probability calculator said 72.87 and a tiny little bit percent, so this is very, very close. And this is a simple calculation. Can be done very quickly on the back of an envelope with no probability calculator, no online text. And it comes out very close. And that's the advantage of the normal approximation to binomial probabilities, and pretty soon we'll see that you can use this kind of approximation to very many other probabilities that we're going to want to find. And even more interesting is that you're not bound to just the fair coin. See, with the fair coin, it is not surprising that the distribution of the number of heads should be symmetric. With an unfair coin, and I'm going to take a coin that's really quite unfair, I'm going to take a die and roll it and call sixes the success. You roll a die 120 times, look at the number of sixes. How many do you expect? 120 rolls times a sixth is the probability of success. You expect 20. And the blue histogram is the probability histogram of the number of sixes in 120 rolls. Now, that's not very beautifully normal, but it is almost. It's getting there. It's not horribly skewed by any means. And so even though we're working with zeros and ones, and it's not half and half zeros and ones, it's 1/6 ones and 5/6 zeros, you still, with 120 trials, see that the probability histogram of the binomial is roughly normal, and should you make more trials, and I went to 240, the normal approximation is better. And should I make even more, 360, 480, or any number that I want, the normal approximation will get better. And I want to repeat, there is no mystery in how these heights have been arrived at. They are just applications of the binomial formula. So this one here is the chance of 40 successes in 240 trials. So that would be 240, choose 40. 1/6 to the 40, 5/6 to the 200. Just straight binomial formula, each and every one of these. So you could have drawn that histogram, and you could also plot the normal curve over it. Now there's a piece of mathematics, of course, that says, in theory, why this approximation works, and that's not a piece of mathematics that we're going to go in at this level. I will just tell you that that piece of mathematics is due to two great mathematicians, de Moivre and Laplace, around 1700s. And what the theorem says is you take any coin you want, as long as it doesn't always give you heads or always give you tails. Those are very boring coins. They always give you the same thing. There's no variation. Take any coin you want and toss it many, many, many times. And roughly what the theorem says is this. As the number of trials increases, the probability histogram for the binomial distribution, in other words, probabilities for the number of successes, begins to look like the normal curve with mean NP and SD square root of NP 1 minus P. In other words, what that's telling you is that if you have a large number of trials and you have a binomial distribution, you can approximate that distribution using the normal curve, whether or not P is a half. And there are some people who are terribly worried at this point, where they're thinking, what does she mean by large? Well, what's large? Hold your horses for a second. We'll do a few hundred for now. Frequently, anything beyond 30 works. In a couple of segments, I'll show you some pointers as to when you know something's large enough. For now, we'll take something really, really large. And this is an example that you've seen before, at least you've seen the setting before. You've got a genetic theory that says that in a species, the plants are red flowering with chance a quarter, independent of all other plants. And you've got lots of plants of these. You've got a field full of them, 10,000 of these. And you want the chance that more than 2,400 are red flowering. And I believe if you tried to use your online calculator, I don't think it would go this far. You certainly don't want to do exact binomial calculations by hand. But what you can do is you can do a normal approximation very swiftly. So the number of red flowering plants among these is the binomial. Number of trials is 10,000, P is 25%, that's what the theory says. And what you're looking for is a number of successes greater than 2,400. So if you're going to use the normal approximation, you first need your prediction. What do you expect the variable to be? What you expect it to be is the number of trials times the probability of success. You expect it to be 2,500. You expect 2,500 plants to be red flowering. Now that's an expectation. There's a plus or minus number to that, and that's the standard error. And the standard error of a binomial is the square root of the number of trials times the probability of success times the probability of failure, and if you work that out, you have about 43. And so now what? So now you look to see, well, what do I want? I want more than 2,400 successes, and so I need to convert 2400 or thereabouts to standard units, and I'm going to be really, really careful, though with numbers that I have, it's not going to make much difference. Because I want more than 2400, my first bar is at 2401. That starts at 2400.5. So I convert that to standard units, and I get essentially negative 2.3. And so what I want is the area under the normal curve to the right of negative 2.3, and the applet tells me that's 98.93%. And I'm done. 4 little moves, and you have a probability involving 10,000 trials. That's a remarkable approximation, and it will be even more remarkable if we could ascertain that it's a good approximation. Now, I used a computer, and the exact chance of getting more than 2400 red flowering is 98.945%, and I stopped there. It's correct to the third place. What do I have here? I have 98.93, very, very good as an approximation, with rather light work. And so that is the huge benefit of the normal approximation, and it turns out things are even better. It's not just the binomial that is roughly normal for a large number of trials. Other probability distributions are roughly normal as well if you have very large samples. And that's the business of the next segment.